So in this video, we're going to focus on the big ideas with graph and rationals. I'm not going to get into the math so much. We're not going to be number crunching. I just want to talk about what these three big concepts are here that I've written here below. What are intercepts, what are restrictions, and what is end behavior as it applies to a rational function in a graph. So first off, let's talk about those intercepts. Intercepts are not changing. These are still x-intercepts and y-intercepts. You can have a whole bunch of them in a function. It kind of just depends on your equation. So you can have many x-intercepts. You can only have one y-intercept, because if you have more than one y-intercept, like a circle that I'm drawing right here, then it's violating the vertical line test. It's not a function. Okay, so rational functions follow the vertical line test. They'll only have one intercept at most. So you can have 0 or 1 y-intercept, and you can have any number of x-intercepts. Okay? The only limit there is how big the equation is that's running this graph. So that's the deal with x and y-intercepts. There's a couple of interactions between those things that are a little oddball, right? Every now and then you see something weird, like, what's this thing? Is it an x-intercept or a y-intercept? Well, it's actually both. So you can have overlapping intercepts. And there's some cases where intercepts actually interact with some of these other ideas, restrictions and end behavior. We need to go over how those work. Now, restrictions are a new idea with rationals. We didn't have these in polynomials. But in a rational function, you have, look at this, you have domain restrictions, either holes or vertical asymptotes. And we've talked in class about how you calculate those things. But what they look like in a graph is, here, let me use red. I'll use red for my restrictions. And I'll just use a vertical solid red line. I usually use dotted lines, but those are a pain in the neck to erase. So I'm just going to use a solid red line. And the function would have to go around these things. It cannot touch a restriction because x cannot exist on a domain restriction. Those are your x does not equal places. So that's what vertical asymptotes look like. Holes have a different look to them. They just look like a donut sort of floating somewhere in your function. So maybe I have a function that, it swoops up at that asymptote. Over here, it comes up from the bottom, and it tries, I went too far with that one. It tries to hit that hole, but remember, that's a restriction. It can't actually touch the hole. So it just sort of jumps over it. And then watch out for the next domain restriction. Sometimes these are on opposite sides, like I have on this one. See how it comes in on opposite sides of the asymptote? That's called an odd symmetry asymptote. Whereas sometimes it's symmetric around the asymptote. You have an even symmetry in that case. And there's reasons for even and odd asymptotes. That's one of the more technical aspects that we went over this in class. It's not one of the important things, though, so I'm not going to spend a whole lot of time talking about that particular behavior. The important thing when it comes to asymptotes is you do not touch them. Okay, so no touchy. Let me say that. No touchy, the vertical asymptote. And with a hole, well, same thing. And you don't touch holes either. So actually, instead of vertical asymptote, I'm just going to say no touchy, the domain restriction. Okay, we will never touch a domain restriction with the function. You're not going to have x-intercepts on the domain restrictions. You're not going to have y-intercepts on the domain restrictions. Your function will never be on those things because they are, by definition, restrictions. Now, there are some asymptotes that don't have the same kind of rules. And horizontal asymptote is one of the easiest examples. You might have seen in this graph, it looks like the function is approaching something, but not quite getting there. Imagine if there were a horizontal line that went across like this. See how the function is approaching it on the left and on the right over here? It looks like it's trying to get close to that function, but it's bending away from the asymptote. So, yeah, we have another kind of asymptote, but this is a completely different beast from a vertical asymptote. Vertical asymptotes are domain restrictions. Horizontal asymptotes are a type of end behavior. They tell us how the function behaves as x becomes very large or very large negative. So either at positive or negative infinity, the ends of the function are approximated with this red horizontal line that goes across. It's sometimes called an end behavior asymptote, actually. Okay, some people call it that. But these end behavior asymptotes come in two varieties. One is a horizontal asymptote, and the other is an oblique asymptote. And you can't have both at once. Okay, you're never going to have a graph with something like this, two asymptotes on it, a horizontal and an oblique. You have to choose. It's going to be one or the other. You might get nothing. You might have no horizontal or oblique asymptote. That's possible. It's rare. Usually you have one or the other. Okay? And there's reasons why you can only have one or the other. It's basically a description of the equation. That's what the asymptote is. It's an approximation of the equation, and the horizontal asymptote is just simply not true for some equations, and the oblique asymptote is simply not true for other equations. That's why you have to choose one or the other. So there's some interesting interactions with the horizontal asymptote. You notice one thing I didn't mention. I said we're avoiding the horizontal asymptote at the ends, but I didn't mention the middle. Look at the middle right here. I'm crossing that horizontal asymptote right here, and that's not a problem. Sometimes you just do that sort of thing. You can have an x-intercept right on a horizontal asymptote, depending on the equation. You could have a hole sitting on a horizontal asymptote. That's possible, right? Maybe this isn't an x-intercept right there at all. Maybe it's a second hole right on that spot on the horizontal. These things can happen depending on the equation. The important thing to remember is horizontal asymptotes are not really asymptotes in the middle. Okay, in the middle they're very squishy. You can just run right through them if you need to. Now I wouldn't just go touching them for fun. You have to have a compelling reason. Like in this graph right here, maybe my compelling reason is that I have an x-intercept right here, and I have a y-intercept over here, and a hole in the middle, and I need to connect those things, and the only way to connect them is by hitting the horizontal asymptote in the middle. So fine, go ahead. Just watch out for it at the ends. That's where it's turning into a real asymptote, an end behavior asymptote, and you want to avoid it. Okay? So, let's see. This is another case of 0 or 1, right? You can only have 0 or 1 end behavior asymptote. So 0 or 1 horizontal, and I'll just say HA/OA. You got to choose one or the other. And let's see. Anything else I'm leaving out here? I think those are the main takeaways of these functions. You'll get more practice with these concepts as you're graphing things, but just remember these basic ideas, and you will avoid certain situations where you accidentally cross a vertical asymptote, right? You're never going to touch those. These are the definite no-touch zone right there. And the end behavior ones, those are just more like guidelines until you get to the ends.